students, I Rajeshwari Shirkanhalli welcome you all in Nagesh Karasgi Orchid School channel. From last few sessions we are discussing chapter number 11 work and energy. In the last session we have completed with our first part of the chapter, that is work, and I introduced to the next concept, that is energy. So we will explore more about energy. So as you know that energy is required for doing each and every kind of work, and this energy is present in different forms. But in this chapter we are mainly going to see two types of energy. They are kinetic energy and potential energy. So life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The ultimate source of energy is sun. But along with sun we get energy from nuclei of atoms, then from under earth's crust, which is called as geothermal energy. We get energy from tides, which is called as tidal energy. So students, after that I told you to do the activity 11.5, in which a few sources of energy are listed above, and you are going to find out some more sources of energy and list them. I hope all of you have done this activity. Now let us move to the remaining part of this. The word energy is very oftenly used in our daily life, isn't it? If suppose somebody in the home, some elder person tell you to do something, sometimes you say that I don't have energy to do that work today, etc. So we use this word energy in our day-to-day life very oftenly, but in science we give it a definite and precise meaning, as we have seen that work done is different which we use in our day-to-day life, but according to science work done is different. Same way here we use energy word always, but according to science it has a definite and precise meaning. So let us consider the following examples. When a fast moving cricket ball hits a stationary wicket, the wicket is thrown away, isn't it? If a ball is moving very fast and if it hits a cricket ball, if that cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. Means in these two examples what we can understand, that a fast moving ball has some energy in it, and here the object which is present at some height is having some energy in it. You must have seen that. So in these two examples we get two different forms of energy, that is kinetic energy and potential energy respectively. Okay, so you have seen that when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood, isn't it? For penetrating the nail into the wood, what we do? We take the hammer and raise it to some height, and then we hit that nail. So when a raised hammer falls on a nail which is placed in the piece of wood, then it drives the nail into the wood, means that nail goes into the wood, it gets penetrated into the wood. We have also observed children winding a toy such as a toy car, and when the toy is placed on the floor it starts moving, isn't it? Some toy cars are working on the key. So what we do? We wind that key, and then if we keep that on the floor it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape, isn't it? When balloon is filled with air, there is a change in the shape of the balloon, and when we press that balloon, air gets expelled out, it goes out of the balloon, and again we can find there is a change in the shape of the balloon. As long as we press it gently, it can come back to its original shape when the force is withdrawn. Okay, so if we press the balloon gently, slowly, then slowly the air starts coming out, and finally the balloon comes to its original shape. However, if we press the balloon hard, it can even explode, producing a blasting sound. Isn't it? If you press the balloon hard, or if you just take a pin and just prick that balloon, you will find that the balloon undergo explosion. It explodes and it produces a blasting sound. In all these examples, the objects acquire through different means the capability of doing work. Isn't it? In all these examples, we find that the objects do work because they get that capability of doing work. An object having a capability to do work is said to possess energy. Okay, so energy is nothing but the capacity to do work. When objects have the capability to do work, means they have energy in them. The object which does the work loses energy, and the object on which the work is done gains energy. So when we do some work, we feel tired. Why we feel tired? Because we lose energy. Okay, so the object which does work loses energy, and the object on which the work is done, it gains energy. Means here one object loses energy and the other object gains energy. How does an object with energy do work? Let us see. An object that possesses energy can exert a force on another object. Okay, so if the object is having energy and then it exerts a force on the other object on which it wants to do the work. When this happens, energy is transferred from the former to the latter. So from the first object, the energy get transferred to the second object. The second object may move as it receives energy and therefore do some work. So in this case, what happens? The first object loses energy and the second object receives, means gains energy, and because of gaining energy, the second object starts moving and it do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. So what can we conclude from this? That any object which has having energy in it can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. So what is energy? It is the capacity of doing work. The unit of energy is therefore the same as that of work. So as the energy possessed by an object is measured in terms of its capacity of doing work, so the unit of energy and unit of work both are same. We have seen that the unit of work is joule, isn't it? So the unit of energy is also joule, which is denoted by a capital J. 1 J, that is 1 joule, is the energy required to do 1 joule of work. Sometimes a large unit of energy called kilojoule, which is written as kJ, is used. So what is 1 kilojoule? It is equal to 1000 joule. How 1 kg means 1000 grams. In the same way 1 kJ means 1000 joules. So 1 joule is the energy required for doing 1 joule of work. So see, work and energy both are related to each other. If you have less energy, you can do less work, and if you have more energy, you can do more work. Means they are directly proportional to each other. Okay, now after knowing this introductory part of energy, let us discuss about forms of energy. Luckily, the world we have provides energy in many different forms. So there are many forms of energy are there, which includes potential energy, kinetic energy, heat energy, chemical energy, electrical energy and light energy. Okay, so these are some examples, some forms of energy. There are many more like geothermal energy, then hydro energy, tidal energy, etc. In this, potential energy and kinetic energy, they are also called as mechanical energy. So, in this chapter we are going to just discuss about only these two forms, that is potential energy and kinetic energy. Now think it over. How do you know that some entity is a form of energy? Just think about it and let me know in the next session. Okay. Now here some information is given about joule. We have just discussed, we know that the unit of work is joule. Similarly, we have discussed now that the unit of energy is also joule. So what is this joule? This name is given in the honor of James Prescott Joule, who born in the year 1818 and passed away in 1889. So see some information about this scientist. James Prescott Joule was an outstanding British physicist. So the scientist of physics is called as physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated the law for the heating effect of electric current. So students, there are three effects of electric current, that is chemical effect of electric current, about which you have learnt last year. Then there is heating effect of electric current, about which you are going to learn in detail in the next year. And the third one is magnetic effect of electric current, about which also you are going to learn in next class, next year. So he did a lot of research on this concept and he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy. You know what is law of conservation of energy? Energy can neither be created nor be destroyed. Only it can be transformed from one form to another form. So the total energy in the universe remains constant. That is called as law of conservation of energy. So he verified this experimentally and discovered the value of the mechanical equivalent of heat. The unit of energy and work called joule is named after him. So this is some information about this great scientist. Now let us see the first form of energy, that is kinetic energy. To understand that, here an activity is given. You can do this activity very easily. What you have to do is take a heavy ball, drop it on a thick bed of sand. A wet bed of sand would be better. Okay, so you can take a bed of sand, you can make it wet by pouring some water on that. Then you have to take a heavy ball and drop it on a thick bed of sand. Drop the ball on the sand bed from heights of about 25 centimeter. The ball creates a depression. Okay, so you have to throw that ball on that sand bed from the height of 25 centimeter. You have to throw it, you have to drop it in the vertically downward direction. When that ball forms on the wet sand bed, it creates a depression. Repeat the same activity from different heights. You can use different heights like 50 centimeter, 1 meter, 1.5 meter and so on. Ensure that all the depressions are distinctly visible. So the depressions should be distinctly visible, and that is why we have to use a wet bed of sand. In the dry bed of sand, the depressions are not clearly visible. So take a wet bed of sand and drop the ball from different heights. First from the height of 25 centimeter, then from the height of 50 centimeter, then 1 meter and then finally from the height of 1.5 meter. Mark the depressions to indicate the height from which the ball was dropped. Compare their depths. Then you have to mark all those depressions and just you can note down or write there the from which height the ball has dropped. Then you can compare their depths. Which one of them is deepest? You will find after doing this activity that the deepest depression is when you throw the ball from the greatest height, that is from the height of 1.5 meter. Which one is shallowest? This is the depression formed when you throw the ball from the height of 25 centimeters. Why? Because moving ball has some energy and that energy gets transferred to that sand bed when it drops, when it falls on the sand bed. So, when the ball is moving from a height of 1.5 meter, it has to move that much height, 1.5 meter. So, it has more energy, and whereas the ball which is moving from just a height of 25 centimeter has less energy in it. What has caused the ball to make a deeper dent? Because of the kinetic energy present in the ball makes the deeper dent. Okay. Now, there is another activity. Set up the apparatus as shown in the figure. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. So, what you have to do in this? You have to set up the apparatus which is shown in figure 11.5. Take a wooden block whose mass should be known and just place it in front of the trolley at a convenient fixed distance. Place a known mass on the pan so that the trolley starts moving. Okay, so what you have to do in this? You have to place the known mass in the pan and you have to ensure that the trolley should move. So, look at the figure. This is figure 11.5. Here this is a trolley and this is a wooden block and this is a pulley, and here a string is passing through this pulley, and here a pan is connected in which you have to keep the masses, different known masses. Okay. The trolley moves forward and hits the wooden block. So, this is the initial position of the wooden block. When we place the masses in this pan, what happens? This pan goes in the downward direction because of that mass present. So, it pulls the string in the downward direction, and because of that this trolley starts moving. It moves in this direction, that is from left to right, and it hits this wooden block. So, after hitting the wooden block, what happens? The trolley stops, but the wooden block is set into motion. The wooden block starts moving. So, you can fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. So, it gets displaced means it changes its position. Note down the displacement of the block. So, here you can see the displacement of the block. This is the original position of the block and this is the new position of the block. So, you can note down this displacement, how much it has got displaced, means how much distance it has moved. This means work is done on the block by the trolley as the block has gained energy, isn't it? Because of this masses in the pan, here the trolley gets energy and that is why it becomes capable of doing work. So, it does work on this block. When it does work, it loses its energy and the block gains the energy, and because of gaining the energy the block gets displaced, it starts moving. Okay. From where does this energy come? This energy has come from the masses which are there in the pan actually. So, repeat this activity by increasing the mass on the pan. In which case is the displacement more? When you increase more masses in the pan, there is more energy given to the trolley and it moves more faster and more work is done in that case. In which case is the work done more? When there is more mass in the pan. In this activity, the moving trolley does work and hence it possesses energy. Now, a moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. Okay, if suppose two same type of objects are there, they are identical to each other, they are having same masses, everything. But if suppose one object is moving faster and the other object is moving slower, means then object which is moving faster can do more work as it consists of more energy, and an object which is moving slow can do less work because it consists of less energy. A moving bullet, blowing wind, a rotating wheel, a speeding stone, these all are the objects which are in motion and they are capable to do work. How does a bullet pierce the target? How does the wind move the blades of a windmill? So, how does a bullet pierce the target? Because the bullet has energy when it is moving, and when it hits the target it pierces in the target. Similarly, the blades of the windmill has energy. Because of the energy of the blade of a windmill, it can move and it can do work. So, objects in motion possesses energy. An object in motion possesses energy. We call this energy as kinetic energy. So, what is kinetic energy? It is the energy which the moving objects have. So, all the moving objects possess energy which is called as kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. So, if you compare, see all these examples, in this all there is a motion, and that is why they all possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. So, if the question is asked to define kinetic energy, what are you supposed to write? Kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. So, if you increase the speed of the object, the kinetic energy of that object increases. Now, how much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a moving body with a certain velocity is equal to the work done on it to make it acquire that velocity. Okay, so, if when an object is in motion, means when a body is moving, how much energy it possesses? To find out that, we have to find out the work done by that moving object, and this work done is equal to kinetic energy. In that way, we can find out the kinetic energy which the moving object is possessing. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on in the direction of its displacement. See students, what are the given things here? The mass of the object is given, that is m, uniform velocity is u, then the distance is s and force is F. From the work done, W is Fs. You know the formula of work done, W is equal to F into S, force into displacement. The work done on the object will cause a change in its velocity. Okay, so, whenever there is an work done on the object, there is a change in the velocity. Let its velocity change from u to v. So, what is u here? The initial velocity, and when the velocity changes to v, v is the final velocity. Let a be the acceleration produced. Okay, so, when there is a change in the velocity, there is some acceleration. Now, in section 8.5, that is in chapter number 8 motion, we studied 3 equations of motion. The relation connecting the initial velocity u, final velocity v of an object moving with uniform acceleration a and displacement s is, we have studied this equation already in chapter 8, that is v square minus u square is equal to 2as. What is v? Final velocity. U is initial velocity, a is acceleration and s is displacement. So, rearrange this equation, you will get s is equal to v square minus u square upon 2a. What we have done? We have just taken this 2a to the LHS. Here there is multiplication, so it will go in the denominator, it gets divided, isn't it? So, S is equal to, that is displacement is equal to V square minus U square upon 2a. Now, in chapter number 9, we have learnt another equation, that is F is equal to ma, means force is equal to mass into acceleration. Thus, using equations 11.2 and 11.1, we can write the work done by the force as, what is 11.1? W is equal to Fs, and 11.2 S value is V square minus U square upon 2a, and F is ma. W is equal to Fs. What is F? That is equal to ma. We can substitute the value of F as ma into S. S value is V square minus U square upon 2a. So, we get W is equal to ma into V square minus U square upon 2a, or W is equal to half m V square minus U square. This 2, if you take it outside the bracket, it is 1 upon 2. This is m as it is. Then this a and this a gets cancelled. So, what do we get? 1 upon 2 m into bracket V square minus U square. If the object is starting from its stationary position, then its initial velocity is 0. We have discussed it in chapter number 8, that if the object is starting from stationary position, means from rest position, then the value of initial velocity is 0, u is equal to 0. So, just put the value of u is equal to 0 in this equation. What do you get? W is equal to half m bracket V square minus 0, means V square. So, we get this final equation, W is equal to half m V square, 11.4. It is clear that the work done is equal to the change in kinetic energy of an object. So, if u is equal to 0, then work done is half mv square. So, thus kinetic energy possessed by an object of mass m and moving with uniform velocity v is half mv square. You know that work done is nothing but the energy possessed in this because of motion. So, kinetic energy is expressed as Ek. So, Ek is equal to half mv square. Is it clear? So, we have used here the formula, that is v square minus u square is equal to 2as. We have rearranged it and we got the formula S is equal to v square minus u square upon 2a. Then we have used the formula W is equal to Fs. We have used the formula F is equal to ma. After substitution of all these, we have got W is equal to ma into v square minus u square upon 2a. Rearranging, we get this, a gets cancelled, we get W is equal to half m v square minus u square. When the object is starting from rest position, that is from stationary position, u value is 0. So, we get W is equal to half mv square. Now, this W is nothing but the kinetic energy possessed by an object for doing this work. So, we get Ek stand for kinetic energy, that is equal to half mv square. So, students, we have derived the expression for kinetic energy. So, this is the formula which you are going to use for solving the numericals. Now, here some examples are given, solve examples which we will discuss in the next class. So, students, today we have discussed that energy is must for doing any kind of work. Okay, so energy is existing in different forms. Law of conservation of energy states that energy can neither be created nor be destroyed, but it can be converted from one form to another form, but the total energy remains constant. But then the question is, why do we always face the problem of energy crisis? Just think about it and tell me the answer in the next session. So, energy exists in different forms. Some forms are light energy, heat energy, chemical energy, nuclear energy, geothermal energy, tidal energy, hydro energy, kinetic energy and potential energy, and so on. But in this chapter we are just going to discuss about potential energy and kinetic energy. We have started with our first type of energy, that is kinetic energy. What is kinetic energy? It is the energy possessed by the objects on account of its motion. Okay, that means all the moving objects have kinetic energy in them. We have derived the expression for kinetic energy. So, what is the formula for kinetic energy? Ek is equal to half mv square, where m is mass and v is velocity. So, today here we will stop. You just go through the concepts, mark the important points and prepare MCQs from these points. We will solve the numericals in the next session, numericals which are based on kinetic energy. Okay, so we will stop here. Thank you.